So thank you, first of all, thank you very much for organizing this amazing Giarè postdoc day. The first thing I want to say is thank you to all the GGI staff for organizing this event, and in general for this great opportunity of working in Florence. And today, in the spirit of reviewing a bit the work I've done here, we will discuss together about the health status of the standard model of cosmology. However, before entering in the details of the talk, I would like to start with some disclaimers about this presentation. And first of all, I would like to start by pointing out that today I will review just a few of the work that I have done here. You can find a full list of all the topics I've been working on this year, and you see that they cover different topics from inflation, gravitational waves, axons, and cosmological tensions. But today I will just review a few of these works, and specifically those on cosmological tensions. And the reason is that I think it's useful, it can be useful for a very diversified audience like this one to have a brief overview about the current situation in cosmology. The second is that, indeed, this talk is set up to reach a broad audience, which means that I will try to explain all the results step by step to reach as many people as possible. And some parts may sound a bit introductive for those of you that are experts in cosmology, and sorry in advance. Finally, the time slot is very short, which means that I'm going to skip most of technical details. But if you have questions, I will be happy to answer. That being said, I would like to start with a brief introduction of our current understanding of cosmology. And our current understanding of the universe is based on the so-called Lambda Cold Dark Matter, or Lambda CDM model of cosmology. I would like to do the exercise of building up this model, starting from its building blocks. What we need is, of course, general relativity and the standard model of particle physics to describe gravitational interactions and interactions between matter and radiation. But we need also three other ingredients: inflation, cold dark matter, and dark energy, that are currently beyond our current comprehension of fundamental interactions. I will say that these ingredients are not very well understood, neither from a theoretical point of view, nor from an experimental side. However, they are crucial to explain observations, because we need inflation, an early period of fast accelerated expansion, to explain spatial flatness and, above all, large-scale homogeneity. We need cold dark matter to explain all the different evidences for a missing mass in the universe and to successfully describe structure formation. Finally, we need a late-time form of dark energy, which we introduce as a cosmological constant term in the Einstein equation, to explain all the observational evidences for an accelerated expansion of the universe. So looking at the slides, you may say that this model looks like a phenomenological data-driven approximation to a more fundamental theory that has yet to be fully understood or even discovered at a more fundamental level. And this is, of course, a possibility, you may be right, but you need to consider that the most remarkable success of Lambda CDM cosmology is that this model is able to provide a spectacular fit to data. And in particular, it is able to provide a spectacular fit to the cosmic microwave background radiation. The cosmic microwave background radiation is a fossil electromagnetic radiation made of relics photons from the Big Bang. It is literally the egg of the Big Bang, in the sense that when the universe was very young, when it was about 380,000 years old, it became transparent to photons. So photons could free stream, and today we can measure these photons all over the sky. And this will result in the most precise black body spectrum ever measured in nature. But we can do better. We can measure the temperature of photons coming from very different regions of the sky, and you will learn that all these photons share the very same temperature unless fluctuations of 1 part over 10 to the power of 5. And the most remarkable success of Lambda CDM cosmology has been to provide a very precise explanations to these tiny temperature fluctuations. And indeed, here you can see the theoretical predictions for the angular power spectra of temperature and polarization anisotropies as predicted by Lambda CDM cosmology, blue line, together with the data points provided by the Planck collaboration. you see that there is a great fit between theory and data at the level that in this plot here, there are just 2 points at more than 2 standard deviations from the best fit line. So we have reached an incredible precision nowadays in cosmology. But this is both a bless and a curse in the sense that what happened in recent years is that as soon as our experimental sensitivity increased and the error bars on cosmological parameters started to narrow, different intriguing tension between CMB and CMB-independent datasets show up at different statistical levels. And today, the most important problem in cosmology is the so-called H0 problem. This is a 5 standard deviation disagreement between the value of the expansion rate of the universe, which is quantified by the parameter H0, as measured by direct measurements at small redshift by supernovae experiments, and as inferred by the cosmic microwave background data. Since we shall see later in this talk, the value of H0 inferred from the cosmic microwave background is somehow sensitive to the underlying cosmological model, this 5 sigma tension is seriously calling into question the correctness of Lambda CDM cosmology. But we don't have only the H0 tension to challenging Lambda CDM. As a matter of fact, in recent years, many different tensions are showing up, of course, at a less significant statistical level. We shall discuss some of these anomalies later on in the talk, but here I would like to point out that we have some mild disagreements both between CMB and CMB-independent experiments and between different CMB measurements. So it's clear that the current situation is motivating both the need of testing Lambda CDM and the need of testing new physics beyond Lambda CDM. When I say testing Lambda CDM, I mean that in this model, we make a certain number of assumptions because we introduce all the 3 unknown ingredients on the basis of simplicity, which means that we want to minimize the number of free parameters in our model. Lambda CDM has just 6 free parameters. If you think, for instance, about the standard model, you realize that this is a quite small number of free parameters. However, one possibility is that the universe is not so simple. And so one way that we can have for testing Lambda CDM is to relax some of the assumptions that we do in this model, fit the data in extended parameter spaces, and check whether we recover Lambda CDM from the fit of the data. Following this spirit, I will now discuss some results that are based on these 3 recent works. And in particular, we will focus exclusively on the measurements of the cosmic microwave background, and we will analyze all the existing measurements of the cosmic microwave background. From one side, we will analyze the Planck 2018 measurements of the cosmic microwave background, since Planck is the most constraining experiment on the cosmic microwave background. But on the other side, we will analyze the Atacama Cosmology Telescope data, the South Pole Telescope data, and the WMAP 9-year observations, combining these 3 datasets in order to reach a sensitivity on parameters which is comparable with Planck. As I told you before, we will analyze this data both in light of Lambda CDM cosmology, but also in light of dozens extended models which differs by Lambda CDM for the inclusion of additional parameters. Our aim is twofold. On one side, we want to check whether we recover Lambda CDM also in extended parameter spaces. And on the other side, we want to test the consistency between independent experiments on the cosmic microwave background. I will start discussing the results from H0, because as I told you, this is the parameter which is raising a certain number of problems in cosmology. And what I want to show with this plot is what I told you before, namely that the value of H0 inferred from the cosmic microwave background is sensitive to the assumptions you do in the model. As a matter of fact, you see that the 5 standard deviation tension with supernovae measurements that you get within Lambda CDM is reduced when you extend the parameter space. Let me stress that this is not a solution to the H0 problem, because what happens in extended parameter spaces is that you simply increase the error bars on H0, and therefore the tension is reduced. This is, of course, not a compelling solution to H naught, but what I want to show is that the value that the tension may rely on the model, because the value of H naught that you infer from Lambda CDM is sensitive to the model itself. Another idea that is growing in recent years is that the universe may not be flat as inflation predicts. And the reason why this idea is growing is that if you analyze the data provided by the Planck collaboration, you systematically get a 3 sigma evidence for an unvanished curvature parameter, which indicates that the universe may not be flat, but curved, closed. However, if you look at CMB data other than Planck, for instance, if you look at the Atacama cosmology telescope combined with W0, you see that this preference never shows up, while it persists for Planck also in extended parameter spaces. So if we trust Planck independent measurements of the cosmic microwave background, then we could conclude that maybe this indication for a closed universe can be explained in terms of statistical fluctuations or observational systematics in the data. And this is, of course, a remarkable possibility. However, what I want to show you now is that Planck and Planck independent measurements of the cosmic microwave background are not so consistent one with the other. And we start from inflation. One of the most remarkable success of the Planck experiments has been to measure this parameter here, which is called NS, which is the spectral index of inflationary perturbations. In most models of inflation, this is expected to be smaller than 1. And indeed, Planck measures NS smaller than 1 at 8 standard deviation. And this has been a great success because it established inflation as the most accredited theory of our early universe. However, if you look at the ACT data, you immediately see that they go instead in the direction of NS equal to 1, introducing a tension with Planck about this parameter at the level of 2.73 standard deviation. You can see in this part here of the plot. In addition, this tension, when projected in this two-dimensional plan, where together with NS we have also the baryon energy density of the universe, you see that the tension increases because also the value of omega baryon measured by ACT is somehow in tension with the value of omega baryon measured by Planck. So this is discussed in the ACT paper. Okay, if you check the paper by ACT, they discuss this tension. And what they say is that basically this tension is due to the fact that ACT doesn't have data points around the first acoustic peak, which means ACT doesn't have data points around this part of the fit. And so this will introduce a degeneracy between the two parameters I showed you before, resulting in these tensions. We have tested this claim, and what we have done is to consider the full ACT data and to split the Planck data between the multiple 600, basically, 650, which will correspond to the part where ACT missed data, and Planck for multiples larger than 650, which will cover the same, basically, the same multiple range that the ACT data. And when you split the Planck likelihood into two parts, you see that Planck is still able to measure NS smaller than 1 at 6 standard deviation, and the tension with ACT is not reduced so much. And you still have the same tension in this two-dimensional plan. So this somehow casts doubts that this preference for a value of NS bigger than 1 can rely on the fact that they don't have data points around the first acoustic peak, because if you remove the points of Planck around the first acoustic peak, Planck still measures NS equal to smaller than 1. Another test that we have done is to combine ACT and South Pole Telescope data. Because if you combine properly, of course, these two experiments, you reach, add other points, and you may eventually break the degeneracy between these two parameters, omega baryon and NS. And indeed, you see the blue contours in this figure, where basically the value of omega baryon when you combine, what happened? I don't know. okay, it solves itself. When you combine ACT with South-Pole telescope data, you see that the value that you obtain for omega baryon now is in full agreement with Planck. However, if you solve the omega baryon, let's say emerging tension, you are not still able to solve the NS tension because the shift toward the NS smaller than 1 is not enough to reconcile this emerging tension. And so you still end up with a 2.5 sigma disagreement with Planck. We performed many other tests, and eventually what we discovered is that the only way you have to reduce the tension below 2 standard deviation is to introduce the possibility that NS is not constant, but may change with the scale, which means it may have a rounding. However, if you do so, you see that the tension on NS is basically reconciled, but now you have a disagreement about the value of the rounding, because Planck prefers a value around 0 for negative values, while ACT gives a 2.67 sigma preference for a positive rounding. Again, this is discussed in the ACT paper. They know that this dataset gives a 2.53 sigma preference for an unvanishing rounding. And what they say is that, okay, but if you again add other CMB data, then you recover the rounding equal to 0, and you are in agreement with Planck again. We tested these claims as well, and what we discovered is that actually, if you parameterize the spectrum up to the second order, you still get a preference for a positive rounding, which is not supported by Planck. So the conclusion we reached in this paper is that there is, in our opinion, a clear emergent tension between what Planck measures for NS, which is fully consistent with inflation, and what ACT is measuring. Of course, this may be anomaly in the ACT data. But this is not the only one, because as a matter of fact, if you check the ACT data, you will discover that there is another anomaly, which is that ACT prefers a small amount of radiation in the early universe, which is quantified by this parameter and effective, which counts basically the number of relativistic particles in the early universe. The standard model predicts this parameter to be basically 3, which will correspond to the 3 families of neutrinos, and Planck is in full agreement with the predictions of the standard model, while by ACT you get a systematic evidence for a small amount of relativistic particles, which persists, as you can see from this plot, even in extended parameter spaces. So the situation is that we have 2 experiments. They are measuring the same observables, the cosmic microwave background angular power spectra, and both datasets have some anomalies that are not supported one with the other. This means that these 2 experiments should be somehow in tension. So what we have done is to apply a statistical methodology, which I will not describe because I don't have time, to quantify the global CMB tension between these 2 independent measurements of the cosmic microwave background, both within Lambda CDM cosmology and for all the other dozens background cosmologies we have analyzed. And we have discovered that, in fact, these 2 experiments are all in tension between 2.5 and 3 standard deviation, depending on the background cosmology. So let me conclude with a takeaway summary. We have a theory, a model, Lambda CDM, we have data, and there is a global agreement between theory and data. However, there are problems because the value of H naught that you infer from the cosmic microwave background, which is somehow model dependent, is in 5 sigma tension with the direct measurements of this parameter. If you focus exclusively on the observations of the cosmic microwave background, you see that while all these observations are broadly in agreement with Lambda CDM, they also give evidence for some anomalies. ACT show a 3 sigma preference for a closed universe. Sorry, Planck show a 3 sigma preference for a closed universe, but ACT doesn't. In its turn, ACT is in 3 sigma tension with Planck about the value of NS, and it also prefers less radiation with respect to the standard model of particle physics. Another point I didn't have to discuss is that ACT gives a 3 sigma preference for early dark energy, which in recent years has been proposed as a solution to H naught problem. So you may find around papers claiming 3 or even 4 sigma evidence for early dark energy. Here, I would just like to stress that these 3 or 4 sigma preference for early dark energy are coming from the ACT data, the same ACT data that are in 3 sigma tension with Planck about NS, and the same ACT data which are in tension with the standard model of particle physics. And in general, the same ACT data which are in 2.6 standard deviation disagreement with Planck. So you may ask, is this the effect of observational systematics, or is this the effect of new physics beyond Lambda CDM? The honest answer is that we don't know, because our analysis is not conclusive in that direction. It just revealed these anomalies that, in our opinion, deserved further investigations, and hopefully future precise CMB measurements may shed light on these anomalies. And here I conclude. Thank you for your attention.
Thank you. Thank you also for the timing.
Yeah, I tried to do my best.
No, okay. Are there questions? Yeah. Otherwise, I don't.
So there is a degeneracy between this measurement of NS and the optical depth of ionization.
We explored extensively that degeneracy, and what we discovered is that actually if you add low-L polarization data, so that you measure tau.
Yeah, I was wondering if it's treated, let's say, ACT and Planck, how they model ionization. The same
way, but ACT is not able alone to measure tau, because it lacks
so that
data
using
point.
that degeneracy might reconcile the data, or
If you no, it may not. If you introduce a prior or use low multiple data, so that also ACT is able to precisely measure tau, then you end up in tension. If you use different parameterization for tau, you are still in tension. We used we did many tests in that direction. We consider different parameterization for the reionization epoch, and we couldn't manage to solve that tension with NS.
So yeah, let me ask you what I have in mind. So if you use the Planck, say, prediction for, say that I fix a model of ionization.
Okay.
I use Planck data to fix tau.
Yes.
The ACT fit.
Exactly.
Would I get a tension or not?
No, it's still there. The tension is still there.
I see. Okay, thanks.
We did that test, exactly that test.
No way.
No way.
No way. Other questions? No? Petta.
If I just look at NS, the tension seems much more. I mean, the evidence for NS less than 1 from Planck is 5 sigma or more.
No, it's not. It's this one. Wait.
Just the.
This is one. This is the Planck measurement, and this is the ACT measurement. They basically are in 2.7 standard deviation tension.
I don't know, I'm reading your paper. NS 0.96 plus or minus 4 10 to minus 3. So
yes, that's Planck, but ACT is a much big error bar.
Ah, okay. So,
no, this is the
disagreement is all on the ACT side. Okay.
Yes, because you have larger error bars from ACT, and so the tension is not so big. But the projection in this two-dimensional plane is big, because also omega baryon is somehow in tension. No? So when you project in the 2D plane, you see that these two contours doesn't overlap.
So ACT is less precise than Planck.
Generally, yes. This may be an ACT anomaly in the data. But the very point of my presentation is that ACT is not so consistent with Planck, because you have this NS problem, you have problems with omega baryon, you have problems with an effective. In general, you are in disagreement with Planck at the level of 2.5, 3 standard deviation, depending on the background cosmology. So this is another, also to say that when you combine ACT and Planck, you are combining two data sets that are not so in good agreement.
So the
and you eventually get
ACT is quite bad for
what?
The chi-square of
the chi-square, we tested the chi-square actually. What we have done is to fit the ACT data, assuming the value of NS measured by Planck, which means we fix NS to the value of Planck, and we fit the ACT data. What happens is the chi-square increase, which means that value of NS equal to those measured by Planck are not prepared by the fit of the ACT data.
Okay.
No other question? No? So, William, thank you very much.
You're welcome.